Hey guys, so in this actual video what we're going to be investigating is the topic called rates of change, and we're going to be doing it from a graphical perspective. So one of the things that you want to do when you're dealing with any kind of a problem that you see rates of change, what you want to think of is immediately going to the graph and start actually labeling it into its different phases. So the way that you do that is you just start over here on the left and you basically just start tracing the graph, and anytime you get to a period where you can't go in a single straight line anymore, that's a whole nother phase of the graph. So right now you can see that I've already colored the first phase right here in kind of a bluish color, and what we're going to do now is come to this next phase, which starts right here and goes to right here, and I'm going to color that in purple. So if we keep walking on this purple phase, we get to this little area of the graph that kind of levels off, and when it levels off, we basically just keep on walking and calling that phase 3. So we keep walking and then we start to see that we go down this section here, so that warrants a whole nother phase of the graph or section. And I'm just going to keep coloring this in, and when I come back from our break here, what I'm going to do is actually start showing you how to calculate the rate of change. Okay, so now that our graph has actually been labeled with all these different areas that we see here, what we're actually going to start looking at is how to calculate the rate of change for each particular area. So the way that you actually deal with calculating rate of change is the first thing that you want to start considering is this idea of something called a change in x and a change in y, or a change in the dependent versus a change in the independent. So if you think about this, if I'm looking at this x-axis right here, and I'm looking at just this phase 1 right here, if you look at it, the start of phase 1 begins at x equals 0, and it goes all the way up to x equals 2. So if you think about this, in terms of how we say change in mathematics, we use a special triangle. This is actually a Greek letter called delta. So what we're saying here is the change in x on phase 1, if I go from 0 to 2, is 2 units. Well, now, looking at this, I can say, okay, so I know what the change of x is for that particular phase, but what's the change in y? Well, if I look at where phase 1 starts, it starts on the y-axis at a height of 0, and when it ends, it's at a height of 3. So I know that that means that the overall change in y is going to be 3 units. Now, recalling from 8th grade that we learned slope is the change in y over the change in x, what I can actually do is relate the same idea. Rate of change is always equal to delta y over delta x, which is very familiar to us from our slope equation. So looking at this, delta y was 3 units, delta x was 2 units, and from that what I can see is these units here will actually cancel, leaving me with just an overall rate of 3 over 2. And this right here would be the actual change for phase number 1. Well, if I wanted to continue this idea for phase number 2, what I would do is just redo all of these same steps here for phase number 2. So looking at phase number 2, I can see that phase number 2 starts at an x value of 2 and goes to an x value of 3, thus giving me a delta x that is going to be equal to 1 unit. So doing all of these steps now in a different color here, I can say for phase 2 I get delta x equals 1 unit, and delta y, we look at phase 2 here, starts at a height of 3 and goes up to a height of 6. Well, that's a total change of 3 units. So then, coming over here, that means that the rate for phase 2 is going to end up being delta y over delta x, and from that what I get is 3 units over 1 unit. Knowing that my units will cancel, that just leaves me with an overall rate of 3 over 1, and if I simplify that down as a fraction, I get 1. So looking at this, we can keep on going, and what I'm really interested in is phase 3 and phase 4. So if we think about this now, phase 3 has a very interesting property here. Okay, if I move this all up just a little bit so I get some more room. Looking at phase 3 starts at an x value of 3 and goes on until I get to an x value of 5. Well, if I go from 3 to 5, that means that delta x down here is going to be equal to 2 units. And then if I look at delta y, when I start in phase number 3. Phase number 3 starts at 6 and ends at 6, which means that my delta y is 0. Well, what this means for the rate here is that if I do delta y over delta x, remember rise over run, change in y over change in x, that's going to give me 0 divided by 2 units. Well, we already know from basic mathematics that 0 divided by anything is just 0. So the rate of change during phase number 3 here is 0. And if you think about this, this line right here is a line that goes perfectly straight across. Well, so does phase number 5 and phase number 9. So what's nice about this is that once you see a horizontal line, you always know that the rate of change will be 0. So right now, we know that this is a 0 rate of change. We know that this right here is a 0 rate of change. And I also know that phase number 9 is also a 0 rate of change. Now, if we look at phase 4, what's actually interesting here is phase 4 starts at an x value of 5 and ends at an x value of 6. So for phase 4, we actually have a nice delta x of 1 unit. So I'm going to come down here and say that the delta x for phase number 4 is equal to 1 unit. Now what I do is I say, okay, in phase 4, I start at a height of 6, and I go down to a height of 5. Well, if I go from 6 to 5, that means that my overall change in y then is going to be negative 1 unit. So the change is negative 1 unit on y, which means that my overall rate now will be expressed as delta y over delta x. And looking at that, I get negative 1 unit over a total of 1 unit. And looking at this, that's going to give us a rate of negative 1. So we now have done most of our phases here, with the exception of phase 6. Phase 6 I'm going to leave as an in-class exercise along with phase number 8. What I'm going to do is phase 10 here and have the idea kind of work over this and say, okay, well, looking at phase 10, that starts at a time of 14, goes to a time of 15. So our delta x for phase number 10 here is going to be, for delta x, we know that that's a change of 1 unit. And then coming down here, we know that it starts at a height of 2 and comes all the way down to a height of 0. So going from 2 to 0 is a change in y of negative 2. So from 2 to 0 is a negative 2 change on my units, which means that my overall rate for phase 10 is actually going to be negative 2 units. Make that look more like a U. Negative 2 units over 1 unit. Knowing that my units will cancel, that means that my rate of change overall for phase number 10 is negative 2. Now, when you're making your calculations here, one of the things that you want to remember here is that a rate of change is actually going to be not really in terms of positive and negative, but when they're saying that it's a positive rate of change, what they're actually saying is that it's positive slope. And we already said that from 8th grade we know that positive slope means that a function is increasing or a graph has increasing values. And then if it's negative slope, we know that the rate of change being negative means that it should be decreasing. What's important to understand is that normally when you're looking at problems that involve rates of change, when they're saying which section has the greatest rate of change, what they're actually saying is not which one has the highest value on a number line, but they're saying which one has the highest absolute value. Because if you think about it, while we look at all these different rates of change here, I see that there's one that has a 3 over 2, one that has a 1, one that has a negative 1, and one that has a negative 2. The actual largest rate of change belongs to this right here, because if I think about these in terms of absolute value, the negative 2 would have the highest value in terms of absolute value, which means that that phase experiences the greatest rate of change. It just happens to be in the negative direction. And if you look at this particular phase of the graph for all the ones that I've calculated, which were phase 10, 5, 3, 9, 1, and 2, and 4, overall, that means that this particular line has the steepest slope. Knowing that, that gives me a good idea that perhaps phase number 8 right here might have an even greater rate of change than phase number 10. I'm going to let you guys calculate that in class, figure out if that's something that you would agree with or disagree with. So if you need any help, feel free to ask, and I will be back with you guys in a second.